A neutron star is a type of stellar remnant that can result from the gravitational collapse of a massive star during a Type II, Type Ab or Type X supernova event. Neutron stars are the densest and tiniest stars known to exist in the universe. Although having only the radius of about 10 km, they may have a mass of a few times that of the Sun. Neutron stars probably appear white to the naked eye. Neutron stars are the endpoints of stars whose inert core mass after nuclear burning is greater than the Chandrasekhar limit for white dwarfs, but whose mass is not great enough to overcome the neutron degeneracy pressure to become black holes. Such stars are composed almost entirely of neutrons, which are subatomic particles without net electrical charge and with slightly larger mass than protons. Neutron stars are very hot and are supported against further collapse by quantum degeneracy pressure due to the phenomenon described by the Pauli exclusion principle. This principle states that no two neutrons can occupy the same place in quantum state simultaneously. The discovery of pulsars in 1967 suggested that neutron stars exist. Born in supernova explosions, these bodies are only 12 to 13 kilometers by radius. In contrast, the Sun's radius is about 60,000 times that. They spin around as rapidly as 716 times a second, or approximately 43,000 revolutions per minute. A typical neutron star has a mass between 1.4 and about 2 solar masses with a surface temperature of 6x105 Kelvin. Neutron stars have overall densities of 3.7 A, 1017 to 5.9 A. 1017 a kilogram per meter 3, which is comparable to the approximate density of an atomic nucleus of 3A, 1017 a kilogram per meter 3. The neutron star's density varies from below 1A, 109 a kilogram per meter 3 in the crust, increasing with depth, to above 6A, 1017 or 8A, 1017 a kilogram per meter 3 deeper inside. This density is approximately equivalent to the mass of a Boeing 747 compressed to the size of a small grain of sand. A normal-sized matchbox containing neutron star material would have a mass of approximately 5 billion tons or 1 km cubed of Earth rock. In general, compact stars of less than 1.44 solar masses the Chandrasekhar limit are white dwarfs, and a compact star weighing between that and 3 solar masses should be a neutron star. The maximum observed mass of neutron stars is about 2 solar masses. Gravitational collapse will usually occur on any compact star between 10 and 25 solar masses and produce a black hole. The smallest observed mass of a black hole is about 3.8 solar masses. Between these, hypothetical intermediate mass stars such as quark stars and electroweak stars have been proposed, but none have been shown to exist. The equations of state of matter at such high densities are not precisely known because of the theoretical and empirical difficulties. Some neutron stars rotate very rapidly and emit beams of electromagnetic radiation as pulsars. Gamma-ray bursts may be produced from rapidly rotating, high-mass stars that collapse to form a neutron star, or from the merger of binary neutron stars. There are thought to be on the order of 108 neutron stars in the galaxy, but they can only be easily detected in certain instances, such as if they are a pulsar or part of a binary system. Non-rotating and non-accreting neutron stars are virtually undetectable. However, the Hubble Space Telescope has observed one thermally radiating neutron star, called RxJ18565-3754. Formation: any star with an initial main sequence mass of around 10 solar masses or above has the potential to become a neutron star. As the star evolves away from the main sequence, subsequent nuclear burning produces an iron-rich core. When all nuclear fuel in the core has been exhausted, the core must be supported by degeneracy pressure alone. Further deposits of material from shell burning cause the core to exceed the Chandrasekhar limit. Electron degeneracy pressure is overcome and the core collapses further, sending temperatures soaring to over 5 billion Kelvin. At these temperatures, photodisintegration occurs. As the temperature climbs even higher, electrons and protons combine to form neutrons, releasing a flood of neutrinos. When densities reach nuclear density of 4 × 10^17 kg per cubic meter, neutron degeneracy pressure halts the contraction. The infalling outer atmosphere of the star is flung outwards, becoming a Type II or Type Ab supernova. The remnant left is a neutron star. If it has a mass greater than about 5 solar masses, it collapses further to become a black hole. Other neutron stars are formed within close binaries. As the core of a massive star is compressed during a supernova, and collapses into a neutron star, it retains most of its angular momentum. Since it has only a tiny fraction of its parent's radius, a neutron star is formed with very high rotation speed, and then gradually slows down. Neutron stars are known that have rotation periods from about 1.4 milliseconds to 30 seconds. The neutron star's density also gives it very high surface gravity, up to 10-13 meters per second 2 with typical values of a few 10-12 meters per second 2. One measure of such immense gravity is the fact that neutron stars have an escape velocity of around 100,000 kilometers per second, about a third of the speed of light. Matter falling onto the surface of a neutron star would be accelerated to tremendous speed by the star's gravity. The force of impact would likely destroy the object's component atoms, rendering all its matter identical, in most respects, to the rest of the star. Properties. The surface of a neutron star is made of iron. In the presence of a strong magnetic field, the atoms of iron polymerize. The polymers pack to form a lattice with density about 10,000 times that of terrestrial iron and strength 1,000,000 times that of steel. It has excellent electrical conductivity along the direction of the magnetic field, but is a good insulator perpendicular to this direction. Immediately beneath this surface the neutron star is still solid, but its composition is changing. Larger nuclei, particularly rich in neutrons, are formed, and materials that on Earth would be radioactive are stable in this environment. With increasing depth, the density rises. When its density reaches 400 billion times that of water, the nuclei can get no larger and neutrons start dripping the unregistered trademark out. As the density increases further, the nuclei dissolve in a sea of neutrons. The neutron fluid is a superfluid. It has no viscosity and no resistance to flow or movement. Within a few kilometers of the surface the density has reached the density of the atomic nucleus. Up to this point the properties of matter are reasonably well understood, but beyond it understanding becomes increasingly difficult. The composition of the core of the star is particularly uncertain. It may be liquid or solid. It may consist of other nuclear particles. And there may be another phase change, where quarks start dripping the unregistered trademark out of the neutrons, forming another liquid. A neutron star has a mass comparable to that of the Sun, but as it is only about 10 km in radius, it has an average density 1 quadrillion times that of water. Such a large mass in such a small volume produces an intense gravitational force. Objects weigh 100 billion times more on the surface of a neutron star than on the surface of the Earth. The intense gravitational field affects light and other electromagnetic radiation emitted by the star, producing significant redshift. The strong gravitational attraction allows neutron stars to spin rapidly without disintegrating. Such spin rates are expected if the core of the original star collapses without loss of angular momentum. If the original star has a magnetic field, then this too may be conserved and concentrated in the collapse to a neutron star. Pulsars, gamma-ray burst sources, and the neutron stars in some X-ray binaries are believed to have magnetic fields with a strength of about 100 million teslas. The gravitational field at the star's surface is about 10-11 times stronger than on Earth. Such a strong gravitational field acts as a gravitational lens and bends the radiation emitted by the star such that parts of the normally invisible rear surface become visible. If the radius of the neutron star is or less, then the photons may be trapped in an orbit, thus making the whole surface of that neutron star visible, along with destabilizing orbits at that and less than that of the radius. A fraction of the mass of a star that collapses to form a neutron star is released in the supernova explosion from which it forms. The energy comes from the gravitational binding energy of a neutron star. Neutron star relativistic equations of state provided by Jim Latimer include a graph of radius versus mass for various models. The most likely radii for a given neutron star mass are bracketed by models April 4 and MS2. BE is the ratio of gravitational binding energy mass equivalent to observed neutron star gravitational mass of m kilograms with radius are meters, AAAAA, given current values. And star mass is m commonly reported as multiples of one solar mass. Then the relativistic fractional binding energy of a neutron star is. A 2 solar mass neutron star would not be more compact than 10,970 meters radius. Its mass fraction gravitational binding energy would then be 0.187, a 18.7%. This is not near 0.6/2 equals 0.3, a 30%. A neutron star is so dense that 1 teaspoon of its material would have a mass over 5.5 a, 1012 a kg, about 900 times the mass of the Great Pyramid of Giza. Hence, the gravitational force of a typical neutron star is such that if an object were to fall from a height of 1 meter, it would only take 1 microsecond to hit the surface of the neutron star, and would do so at around 2,000 kilometers per second, or 7.2 million kilometers per hour. The temperature inside a newly formed neutron star is from around 1011 to 1012 Kelvin. However, the huge number of neutrinos it emits carry away so much energy that the temperature falls within a few years to around 106 Kelvin. Even at 1 million Kelvin, most of the light generated by a neutron star is in X-rays. In visible light, neutron stars probably radiate approximately the same energy in all parts of visible spectrum, and therefore appear white. The pressure increases from 3 A, 1033 to 1.6 A, 1035 pascals from the inner crust to the center. The equation of state for a neutron star is still not known. It is assumed that it differs significantly from that of a white dwarf, whose EOS is that of a degenerate gas which can be described in close agreement with special relativity. However, with a neutron star the increased effects of general relativity can no longer be ignored. Several EOS have been proposed and current research is still attempting to constrain the theories to make predictions of neutron star matter. This means that the relation between density and mass is not fully known, and this causes uncertainties in radius estimates. For example, a 1.5 solar mass neutron star could have a radius of 10.7, 11.1, 12.1 or 15.1 kilometers. Structure. Current understanding of the structure of neutron stars is defined by existing mathematical models, but it might be possible to infer through studies of neutron star oscillations. Similar to asteroseismology for ordinary stars, the inner structure might be derived by analyzing observed frequency spectra of stellar oscillations. On the basis of current models, the matter at the surface of a neutron star is composed of ordinary atomic nuclei crushed into a solid lattice with a sea of electrons flowing through the gaps between them. It is possible that the nuclei at the surface are iron, due to iron's high binding energy per nucleon. It is also possible that heavy element cores, such as iron, simply sink beneath the surface, leaving only light nuclei like helium and hydrogen cores. If the surface temperature exceeds 106 Kelvin, the surface should be fluid instead of the solid phase observed in cooler neutron stars. The atmosphere of the star is hypothesized to be at most several micrometers thick, and its dynamic is fully controlled by the star's magnetic field. Below the atmosphere one encounters a solid crust. This crust is extremely hard and very smooth, because of the extreme gravitational field. Proceeding inward, one encounters nuclei with ever-increasing numbers of neutrons. Such nuclei would decay quickly on Earth, but are kept stable by tremendous pressures. As this process continues at increasing depths, neutron drip becomes overwhelming, and the concentration of free neutrons increases rapidly. In this region, there are nuclei, free electrons, and free neutrons. The nuclei become increasingly small until the core is reached, by definition the point where they disappear altogether. The composition of the superdense matter in the core remains uncertain. One model describes the core as superfluid neutron degenerate matter. more exotic forms of matter are possible, including degenerate strange matter, matter containing high-energy pions and quarks in addition to neutrons, or ultra-dense quark-degenerate matter. History of discoveries. In 1934, Walter Baade and Fritz Zwicky proposed the existence of the neutron star, only a year after the discovery of the neutron by Sir James Chadwick. In seeking an explanation for the origin of a supernova, they tentatively proposed that in supernova explosions ordinary stars are turned into stars that consist of extremely closely packed neutrons that they called neutron stars. Baade and Zwicky correctly proposed at the time that the release of the gravitational binding energy of the neutron stars powers the supernova. In the supernova process, mass and bulk is annihilated. Neutron stars were thought to be too faint to be detectable and little work was done on them until November 1967, when Franco Pacini pointed out that if the neutron stars were spinning and had large magnetic fields, then electromagnetic waves would be emitted. Unbeknown to him, radio astronomer Anthony Hewish and his research assistant Jocelyn Bell at Cambridge were shortly to detect radio pulses from stars that are now believed to be highly magnetized, rapidly spinning neutron stars, known as pulsars. In 1965, Anthony Hewish and Samuel Ekwar discovered an unusual source of high radio brightness temperature in the Crab Nebula. This source turned out to be the Crab Nebula neutron star that resulted from the Great Supernova of 1054. In 1967, Iosif Shklovsky examined the X-ray and optical observations of Scorpius X1 and correctly concluded that the radiation comes from a neutron star at the stage of accretion. In 1967, Jocelyn Bell and Anthony Hewish discovered regular radio pulses from CP 1919. This pulsar was later interpreted as an isolated, rotating neutron star. The energy source of the pulsar is the rotational energy of the neutron star. The majority of known neutron stars have been discovered as pulsars, emitting regular radio pulses. In 1971, Riccardo Giacconi, Herbert Gorski, Ed Kellogg, R. Levinson, E. Schreier, and H. Tannenbaum discovered 4.8-second pulsations in an X-ray source in the constellation Centaurus, CEN-10-3. They interpreted this as resulting from a rotating hot neutron star. The energy source is gravitational and results from a rain of gas falling onto the surface of the neutron star from a companion star or the interstellar medium. In 1974, Anthony Hewish was awarded the Nobel Prize in Physics for his decisive role in the discovery of pulsars without Jocelyn Bell, who shared in the discovery. In 1974, Joseph Taylor and Russell Hulse discovered the first binary pulsar, PSAB 1913+16, which consists of two neutron stars orbiting around their center of mass. Einstein's general theory of relativity predicts that massive objects in short binary orbits should emit gravitational waves, and thus that their orbits should decay with time. This was indeed observed, precisely as general relativity predicts, and in 1993, Taylor and Hulse were awarded the Nobel Prize in Physics for this discovery. In 1982, Don Backer and colleagues discovered the first millisecond pulsar, PSAB 1937+21. This object spins 642 times per second, a value that placed fundamental constraints on the mass and radius of neutron stars. Many millisecond pulsars were later discovered, but PSAB 1937+12 remained the fastest spinning known pulsar for 24 years, until PSAJ 1748-2446 AD was discovered. In 2003, Marta Bergau and colleagues discovered the first double neutron star system where both components are detectable as pulsars, PSAJ 0737-3039. The discovery of this system allows a total of 5 different tests of general relativity, some of these with unprecedented precision. In 2010, Paul Damarest and colleagues measured the mass of the millisecond pulsar PSAJ 1614 to be 1.97 A plus or minus 0.04 solar masses, using Shapiro delay. This was substantially higher than any previously measured neutron star mass, and places strong constraints on the interior composition of neutron stars. In 2013, John Antoniadis and colleagues measured the mass of PSJ 0348 plus 0432 to be 2.01 A plus or minus 0.04 solar masses, using white dwarf spectroscopy. This confirmed the existence of such massive stars using a different method. Furthermore, this allowed, for the first time, a test of general relativity using such a massive neutron star. Rotation: neutron stars rotate extremely rapidly after their creation due to the conservation of angular momentum. Like spinning ice skaters pulling in their arms, the slow rotation of the original star's core speeds up as it shrinks. A newborn neutron star can rotate several times a second. Sometimes, the neutron star absorbs orbiting matter from a companion star, increasing the rotation to several hundred times per second, reshaping the neutron star into an oblate spheroid. Over time, neutron stars slow down because their rotating magnetic fields radiate energy. Older neutron stars may take several seconds for each revolution. The rate at which a neutron star slows its rotation is usually constant and very small. The observed rates of decline are between 10^10 and 10^21 seconds for each rotation. Therefore, for a typical slowdown rate of 10 or 15 seconds per rotation, a neutron star now rotating in 1 second will rotate in 1.000003 seconds after a century, or 1.03 seconds after 1 million years. Sometimes a neutron star will spin up or undergo a glitch, a sudden small increase of its rotation speed. Glitches are thought to be the effect of a star quake. As the rotation of the star slows down, the shape becomes more spherical. Due to the stiffness of the neutron crust, this happens as discrete events when the crust ruptures, similar to tectonic earthquakes. After the starquake, the star will have a smaller equatorial radius, and since the angular momentum is conserved, rotational speed increases. Recent work, however, suggests that a starquake would not release sufficient energy for a neutron star glitch. It has been suggested that glitches may instead be caused by transitions of vortices in the superfluid core of the star from one metastable energy state to a lower one. Neutron stars have been observed to pulse radio and X-ray emissions believed to be caused by particle acceleration near the magnetic poles, which need not be aligned with the rotation axis of the star. Through mechanisms not yet entirely understood, these particles produce coherent beams of radio emission. External viewers see these beams as pulses of radiation whenever the magnetic pole sweeps past the line of sight. The pulses come at the same rate as the rotation of the neutron star, and thus, appear periodic. Neutron stars which emit such pulses are called pulsars. The most rapidly rotating neutron star currently known, PSJ 1748-2446 AD, rotates at 716 rotations per second. A recent paper reported the detection of an X-ray burst oscillation at 1122 Hz from the neutron star XTEJ 1739-285. However, at present, this signal has only been seen once, and should be regarded as tentative until confirmed in another burst from this star. Population and distances: at present, there are about 2,000 known neutron stars in the Milky Way and the Magellanic Clouds, the majority of which have been detected as radio pulsars. Neutron stars are most concentrated along the disk of the Milky Way, although the spread perpendicular to the disk is large because the supernova explosion process can impart high speeds to the newly created neutron star. Some of the closest neutron stars are RxJ 1856.5-3754 about 400 light-years away and PSJ 0108-1431 at about 424 light-years. RxJ 1856.5-3754 is members of a close group of neutron stars called the Magnificent Seven. Another nearby neutron star that was detected transiting the backdrop of the constellation Ursa Minor has been nicknamed Carver by its Canadian and American discoverers, after the villain in the 1960 film The Magnificent Seven. This rapidly moving object was discovered using the ROSAT Bright Source Catalog. Binary neutron stars: about 5% of all known neutron stars are members of a binary system. The formation and evolution scenario of binary neutron stars is a rather exotic and complicated process. The companion stars may be either ordinary stars, white dwarfs or other neutron stars. According to modern theories of binary evolution, it is expected that neutron stars also exist in binary systems with black hole companions. Such binaries are expected to be prime sources for emitting gravitational waves. Neutron stars in binary systems often emit X-rays, which is caused by the heating of material accreted from the companion star. Material from the outer layers of a companion star is sucked towards the neutron star as a result of its very strong gravitational field. As a result of this process, binary neutron stars may also coalesce into black holes if the accretion of mass takes place under extreme conditions. It has been proposed that coalescence of binaries consisting of two neutron stars may be responsible for producing short gamma-ray bursts. Such events may also be responsible for creating all chemical elements beyond iron, as opposed to the supernova nucleosynthesis theory. Subtypes: neutron star, protoneutron star, theorized. Radio-quiet neutron stars, radio-loud neutron star, single pulsars, a general term for neutron stars that emit directed pulses of radiation towards us at regular intervals. Rotation-powered pulsar, magnet era, a neutron star with an extremely strong magnetic field, and long rotation periods. Soft gamma repeater, anomalous X-ray pulsar. Binary pulsars, low-mass X-ray binaries, intermediate-mass X-ray binaries, high-mass X-ray binaries, accretion-powered pulsar, X-ray burster, a neutron star with a low-mass binary companion from which matter is accreted, resulting in irregular bursts of energy from the surface of the neutron star. Millisecond pulsar, sub-millisecond pulsar. Exotic star, quark star, currently a hypothetical type of neutron star composed of quark matter, or strange matter. As of 2008, there are 3 candidates. Electroweak star, currently a hypothetical type of extremely heavy neutron star, in which the quarks are converted to leptons through the electroweak force, but the gravitational collapse of the star is prevented by radiation pressure. As of 2010, there is no evidence for their existence. Preon star, currently a hypothetical type of neutron star composed of preon matter. As of 2008, there is no evidence for the existence of preons. Giant nucleus, a neutron star has some of the properties of an atomic nucleus, including density and being composed of nucleons. In popular scientific writing, neutron stars are therefore sometimes described as giant nuclei. However, in other respects, neutron stars and atomic nuclei are quite different. In particular, a nucleus is held together by the strong interaction, whereas a neutron star is held together by gravity, and thus the density and structure of neutron stars is more variable. It is generally more useful to consider such objects as stars. Examples of neutron stars: PSJ 0108-1431, closest neutron star; LGM1, the first recognized radio pulsar; PSRB 1257+12, the first neutron star discovered with planets; Swift J 1756.9-2508, a millisecond pulsar with a stellar-type companion with planetary range mass; PSRB 1509-58, source of the Hand of God photo shot by the Chandra X-ray Observatory; PSJ 0348+0432, the most massive neutron star with a well-constrained mass. See also. Notes. References. External links: Introduction to Neutron Stars for Undergraduates and its Errata, NASA on Pulsars, NASA sees hidden structure of neutron star in Starquark. SpaceDaily.com. April 26, 2006, mysterious X-ray sources may be lone neutron stars. New Scientist. Massive neutron star rules out exotic matter. New Scientist. According to a new analysis, exotic states of matter such as free quarks or BECs do not arise inside neutron stars. Neutron star clocked at mind-boggling velocity. New Scientist. A neutron star has been clocked traveling at more than 1500 km per second.